Hello, welcome to another topic of our AI class. And in this video, I would like to talk about decision tree, which is one of the quite useful model and also a building block for another popular model called random forest. Okay, so let's get going. Okay, so this decision tree is a classification model. So its job is to classify your sample, right? For example, if you have like sample one, sample two, like sample three, and so on. You wanna classify. So give all of this some class, right? And I guess before we were talking about some mathematic model of how you would, like, for example, if it's like logistic regression, you would draw a line in the attribute space, right? Draw a straight line to split the sample in the decision surface that you would see on the graph, our two-dimensional graphs, right? This one is very simple in a way that each of the sample will have attributes, like for example, attribute one, right? Attribute two, and so on, right? And if you want to classify all of this sample, right? You just look at the attributes, right? And you come up with a condition. For example, like maybe you want a1 equal larger than 10. You classify that sample as one class, and if a1 is greater than 10, you tag it with another class or something like that, right? So you simply kind of test the attribute with certain conditions, and you just kind of separate your sample in that way, which is kind of a very intuitive way that we would do, right, in our head, for example. So essentially you ask some questions that are related to the attributes, and then you making decision or classification, assigning the class based on the answer of that conditions. Okay, something that like questions that you can ask is like, is true or false? Is the weather sunny? And in this case, you would imagine that the sunny, the type of weather is it's the attributes, and then this is the condition. And if the sample I guess has the attribute that satisfy this condition, you would give it this class, right? And then if it doesn't, then you would give it another class, right? This one might be a bit not related to what we're doing, but for something like this would make more sense, right? If you want to build the model that kind of predict if you want to go see doctor or not, then you would look at the heart rate, for example. That will be your attributes, right? And if the heart rate is greater than 100 BPM, then you classify that information or that sample as this class, see doctor class. And if it's not, then this is another label or class, right? So, in this example, there is only one question, right? But then I guess in a more complex classification, then you might want to have something like this, which is several series of questions. So maybe you ask the first question, and you kind of split your sample into two bins, one here and one here. But then maybe this one is okay. You are satisfied with how this group already. But then you might want to classify this group into a further subdivisions, and then you would ask more questions, and then you might split your sample into three more subclasses, I guess three more labels, and then maybe you satisfy with this label and this label already, so you're done. But then the sample that fall into this label can be classified further and goes into this label, right? And if you look at this, you can kind of see that it kind of looks like the tree, but it's upside down, which I kind of pointed out in this image. So I guess that's where the name decision trees come from, because it's like a tree, although upside down, and then you kind of make decision or classification based on the tree, I guess. Okay, so far so good, right? But then, I mean, if we were to do this manually, then I guess we can kind of do this by just looking at the sample by eyes, and then kind of give them the class by looking at the attributes, right? But then if you want to make this into like a machine learning model, then you kind of have to find a mathematical way of describing this behavior. Especially if you remember, like in all of the classification model, we have something called cost function, right? Like for example, logistic regression, there's a cost function for it, right? And then we talked about the fact that the machine learning problem is the optimization problem, right? Because what we need to do is that once we have the mathematical description of this, we wanna minimize this, right? With a certain constraints, right? So essentially, I guess the a very clever way, or the things that I find it very cool about decision tree, is that there's a way to kind of encapsulate all of this logic into a mathematical cost function, and then we can optimize it with the optimization schemes. So that's where this thing come from, right? So in the process of making the decision tree, which is the machine learning, we don't have to do it manually. It kind of do it automatically using the something called the description of the information gain. So that is kind of like the crux of the whole thing, is that there has to be a way of describing what question makes sense, or if this question should be used or not. And the criteria or the cost function that is used is based on the information gain. Okay, so this one sounds a bit kind of abstract. So let me just show you the link to the information gain. It's quite mathematical because it deals with the kind of like the combination or the way that you can kind of arrange things. So if things are mixed up, then the information gain is less. But if you can make things separate, that means that it's the information again increases, something like that. And it deals with the concept of entropy. Okay, like this. Okay, so it's a bit abstract. So if you wanna go into it, I guess another way you can do is search on YouTube. I think there are. I learned about this concept first from YouTube because it's kind of give me the overall idea before you dive into all this mathematical equation. It can be quite intimidating, but I guess at this point or at this level, I think all you need to do is that this is a way for the model. I guess this is a way to quantify the cost function and max I guess and optimize that cost function in a mathematical ways. Okay, right? So if so with this I guess with this scheme, then we can kind of like building the tree automatically by using this optimization scheme. And then once the tree is constructed automatically for us, then there are also a method to prune. I guess it's borrowed from the way that we cut the trees, but there's a way that you can kind of trim things so that it's more generalized to new data. Okay. All right. So in order to use the decision tree in scikit-learn, it's quite simple. You just have to load the class and then initialize the object instance. But the I guess the parameter that you might want to take a look at is the something called the criterions. Okay, and then when you use the criterion, there are I guess two options you can use. One is called Gini, and the other one is entropy. I guess if you look at this, then you might be guessing that entropy, I just mentioned it, right? It's something to do with the information gain. So these two options deal with how you actually measure the information gain once you ask the questions. Okay. And I guess in my experience, it doesn't make that much difference, but the default is Gini. So if you want to take a look into Gini, you can search Google for what this is doing. There is a little bit difference in terms of Gini and entropy, but they're quite similar. I guess from my experience, they're not that doesn't affect the result that much. Okay. The next one actually quite important is called max depth. Okay. So it's the tree depth, right? So this is how many levels of the tree that you allow. I guess that you allow to happen. For example, if you have max depth equal to a very high number, you're gonna have more layer, so you can have more questions. I guess if you have very few layers, for example, if max depth is 1, then that means that you only allow 1 questions. So as you can imagine, that if you set max depth to be very, very low, then I guess the ability to classify might be less. If you set max depth to be a lot, then I guess the tree will have more ability to classify. right? And you might be wondering, like, why do we want max depth to be small? Like, why would you want our classifier to be stupid, right? There is a use case for that, and for that, we're gonna have to go to random forest subsequently, okay? But right now, if you want your classifier to be, I guess, to be smarter, then you might wanna make max depth to be, some, I guess, not too small, I guess. And I guess there is also something called none. The default value is none, which is, I guess, make it almost like infinite. So run until you can split the sample perfectly. So that is the default value for max depth. But you can certainly set to something like maybe 10, like or 6. Maybe that is something that I would also try, like 10, 6 to 10 or something like that too. Okay. And then the mean number of mean sample split. So that is the number of sample that you would require to split the node. So for example, this is the number that that the system used to decide if it should ask more questions or not. For example, like this node right here, right? I was saying that this node, you might want to split them further into 3 sub problems, sub categories, right? But then if the number of sample that stay in this bin is less than this number, the min sample split, then the system will not ask any more questions. So that is another kind of like the way to prevent the I guess too many questions, for example. Okay, so I guess 2 would be okay, but you can certainly increase this number. If you increase more to maybe like 6 or 10 or something like that, then the level or the depth of the tree also will be reduced. Okay, so 2 is okay, unless you have you want to try something else, I guess larger, then you can certainly try that. Okay. All right, so I guess we'll try that with our iris data, and we'll try a couple parameters, or for example the criterion, max depth, and min sample split. Okay, so we'll see you later.